All right, now, in the previous segment, we saw how to compute PPMI, positive pointwise mutual information. In this segment, we'll see how to take those values and compute similarity between words. First, let's talk about a different kind of context than just word context. A common way to define context is to use syntax. And this again relates back to early linguistic arguments that the meaning has to do with the restriction of combination of entities grammatically. So in other words, two words are similar if they have similar parse context. And we haven't talked a lot about parsing, but to give you the intuition, the words duty and the words responsibility can both be modified by similar adjectives. So we can have additional duty, administrative duty, assumed duty, or additional responsibility, administrative responsibility, assumed responsibility. And they can also be objects of similar verbs: assert duty, assign a duty, assume a duty, assign a responsibility, assume a responsibility. So it's not just that they have similar words around them, but that their grammatical context can be similar. They have similar parse context. And we can capture this by using co-occurrence vectors that are based on syntactic dependencies. So we say that the context, instead of being counts of words with previous 10 words or following 10 words, the context instead are how many times I have a particular word as my subject, or how many times I have a particular word as my adjectival modifier. So here's an example from Dekang Lin. We have the word sell, and we say, how often was this the subject of the verb absorb? Well, once. How often was it the subject of the verb adapt? How about the subject of the verb behave? How about the prepositional object of the verb inside? So we can get our counts for each of these contexts. And now our vector is determined not by counts of words that occur within 10 words of me, but counts of times I occur in a particular grammatical relation with a context. And just as we saw with word counts, we can use PMI or PPMI to our dependency relations. So the intuition comes from early work by Don Hindle. If I count in a corpus and I parse the corpus and I see that the verb drink has the object it 3 times, and it has I drink anything 3 times, I drink wine twice, I drink liquid twice, and so on. Well, drink it or drink anything are in fact more common than drink wine. But we'd like to say that wine is a more drinkable thing than it. If I found a wine occurring a lot with a verb, 2 different verbs, I would think that those verbs are probably similar, more than if I found it occurring as the object of the 2 verbs. And if I compute the PMI between the object of the verb and the verb drink, now I see that wine and tea and liquid have a much higher PMI than it or anything. So if I sort by PMI, now I see that tea and liquid and wine are the most associated words to be the object of the verb drink. So PMI used for noun associations, just for words in the context, for word associations of word in the context, and also for associations for dependency relations. All right, now we've seen how to compute the term context or word context matrix, how to weight it with PMI, and we talked about computing it in 2 ways based on just words that are in my neighborhood of 10 words, or whether I'm in a particular syntactic or grammatical relationship with words. Now we're ready to use those to compute the actual similarity. And the cosine metric, we're going to use just the same cosine that we saw from information retrieval. So remember, we had a dot product. We said that the cosine similarity between 2 vectors indicating the counts of words, is just the dot product between, the similarity is the dot product between the 2 words normalized by the length of the 2 vectors. So the dot product v dot w over length of v times length of w. Or we could think of it as computing separate unit vectors, the normalizing v by its length, normalizing w by its length to get unit vectors, and just multiplying them together. Or we can compute the whole thing out. So here's our dot product for each dimension of v and each dimension of w. We multiply the values together, and then we normalize by the square root of the sum squared values to get the length of the vectors. And now, let's say we're doing PPMI, so v sub I is the PPMI value for word v in context I, and w sub I is the PPMI value for word w in context I. And remember that cosine as a metric, if 2 vectors are orthogonal, they're going to have a cosine of 0. If they point in opposite directions, they'll have a cosine of -1. If they point in the same direction, they'll have a cosine of +1. And it turns out that raw frequency or PPMI are non-negative. They're always 0 or greater. So that means that the cosine range is always 0 to 1. We're always on this part of the slope. So cosine as a similarity metric, if we use PPMI weighted counts, we're going to get, or raw frequency for that matter, we're going to get a number between 0 and 1. So let's use cosine to compute similarity, and I've taken a little subset of the example we saw earlier. So we have apricot, digital, and information. And we have the context vector, we have large, data, and computer. And I'm just going to use counts here instead of PPMI values just for making the example more simple to see. But in real life, of course, we'd use PPMI. So the cosine between apricot and information is the dot product. So from apricot to information, we have 1 times 1 plus 0 times 6 plus 0 times 1, or 1 plus 0 plus 0, over the square root of the length of apricot, 1 squared plus 0 squared plus 0 squared, over the length of information, 1 squared plus 6 squared plus 1 squared. And that's going to be 1 over the square root of 38, or 0.16. And similarly, the cosine between digital information, we have from digital to information, we have 0 times 1 plus 1 times 6 plus 2 times 1. So that's going to be 0 plus 6 plus 2 over the square root of the length of digital. So that's the length of digital, I'm sorry. So that's square root of 0 squared plus 1 squared plus 2 squared. So root of 0 plus 1 plus 4. And then the length of information, the same as we saw before. And now we get 0.58. And similarly for apricot and digital, now the dot product between apricot and digital, 1 times 0, 0 times 1, 0 times 2 is 0. So we're going to get a similarity of 0. There are a number of possible similarity metrics. Besides cosine, we can use the Jacquard method that we saw earlier in information retrieval, the dice metric, or there's a family of information theoretic methods like Jensen-Shannon divergence that can be also used for similarity. But cosine is probably the most popular. Similarity for distributional methods is evaluated just the same as it is for thesaurus-based methods. Either intrinsic evaluation, where we compute its correlation with some human number, human word similarity number, or extrinsically we pick some task like taking the TOEFL exam or detecting spelling errors, where we can compute some error rate, and now we see if our similarity metric results in a better error rate. In summary, distributional similarity metrics use a method of association like PPMI and a metric for similarity like cosine to give you a similarity between two words. And distributional and thesaurus-based methods both very useful in deciding if two words are similar for any NLP application.